All right, so we're going to, a few reminders first. So no office hours today or tomorrow. I don't know if I spelled tomorrow right. Nope. I don't know. All right, but no office hours. That would be Wednesday or Thursday. Exam review is still on Friday. Fleming 160, same story as always. The third midterm is going to still be as planned. Beginning of chapter 7 to the 296, which we'll finish today. So everything that we cover today will be on the exam, but anything after that on Friday or next week obviously won't be. So we are a little bit ahead of the other sections, so we're going to go ahead with the exam as planned to cover up to 96. And I think that's all I have for reminders. Oh, one more thing. Course evaluations are going to be Friday now because they were supposed to be Monday of this week. So course evaluations are this Friday, 4/22. So in addition to getting a whole day off this week, you'll also get about 20 minutes off on Friday. Although you will be expected to do the evaluations, I hope you will. And please be here for that. Okay. So with that, let's get started with what we have left. So last time we talked about the first two types of cubic structures for metals, and now we're going to finish with the third type, which is face-centered cubic, also called cubic close-packed. All right, so this one is perhaps a little bit more difficult to visualize, especially from a layered perspective. So, we talked about last time how we can build all these structures by taking two-dimensional layers of atoms and stacking them on top of each other. This one, we do what's called BCA packing, and here we're starting with what's called a close-packed layer. All right, so before when we stacked the atoms in layers, remember they were all right on top of each other. This time, if you notice, the first row here is all lined up, and then the second row sort of fits into the dimples created by the first row. So they're packed closer together, similar to what you would do if you were, racking up pool balls to play a game of billiards or something. So they're all as close together as possible. So we call it a close-packed layer. So that's one difference. What we saw when we made the primitive cubic structure, the layers were, the rows were eclipsed, so there was one row right on top of each other, and then when we made the body-centered cubic structure, there was a space between all the atoms in each layer. But here we have the spheres as close together as is physically possible in a two-dimensional arrangement. And then what we're going to do is we're going to stack them on top of each other. So the first layer, which we'll call A, I'm showing in yellow here, okay? And then the second layer is going to go onto the gaps created by the first layer. So there's these little triangular gaps here that we're going to put the next layer over top of. And then the third layer, which is shown in green, is going to be still on top of the gaps from the second layer. So we're not going to totally eclipse the first layer until we get to the fourth one. So this is what we call BCA packing. So yellow is A, blue is B, and then green is C. And then when we have this, we have A, B, C, A. So you don't actually stack the fourth layer, you don't actually eclipse the first layer until you're in the fourth layer. So the first three layers are all sort of staggered from each other, and then you put this fourth layer directly above the first layer. That's what we call it, ABC or ABCA, it's sometimes called as well. Okay, and then to sort of see how we get a face-centered cube out of this. So face-centered cubic means we have atoms at all corners of the cubes, and then we have one atom in the center of each of the six faces. And that's why we call it face-centered. It's a little bit hard to visualize from the layer structure because here we have to take these layers and sort of turn them over 45 degrees, and then the cube sort of, as you go from layer to layer, you run through the diagonal of the cube. So it's not the easiest one to visualize, but if you take my word for it, when you do an BCA packing, you get a face-centered cubic structure. A lot of different ways of visualizing that on this slide here. Now, just like we saw for the rest of the structures, we can sort of define a packing density and other parameters of this related to the atomic radius of whatever's occupying this structure. So here what we need is, we're in a face-centered cubic arrangement. So if we look at one face of our cube up here, you have an atom in the corner. As you go from the diagonal of the face, you have one in the corner, one in the center, and then another one in the corner. So what I'm showing here is sort of a two-dimensional cutout of one of the faces of the cube. So this is the side length A, which we define as the length of the side for the cube. And then as we run through the diagonal here, we have one radius for the corner atom, we have 2r to go through the center, and another radius. So from geometry, the length of a face diagonal now we're talking about is just Pythagorean theorem, a squared plus a squared is equal to the length of the diagonal squared, which means the diagonal is a radical 2. And we also saw that this diagonal a radical 2, we have to go through 4 radiuses, 4r, to get there. So a radical 2 is 4r, which means in this case, the length of a side in terms of the atomic radius is 4r over radical 2, which is 2 radical 2 times r. Okay, so this time we have to in order to accommodate the atom in the center of the face here, we have to sort of expand this out. You'll notice that there's now a gap between the 2 corner atoms to accommodate this one in the center. The number of spheres per unit cell, so we learn how to count the different positions in a cubic cell and how many atoms they count as, depending on how many cells they're shared with. So we have the corners are still occupied, all 8 corners, and each of those counts as 1/8 of an atom, because each corner is shared by 8 adjacent unit cells. So those are the corners. And then on the faces, the cube has 6 faces. 1, 2, 3, 4 are on the side, and then the 2 on the top and bottom. So there's 6 faces. Each of those has an atom in it. And remember, a face is shared between 2 cubes. So when you stack the cubes right next to each other, they come together face to face. So any atom that's on the face is going to count as half of an atom. We talked about that last time. So these are the faces, which means in total there's 4 atoms per unit cell in the face-centered cubic structure. And that means the volume of the spheres then, the total volume of all the atoms, we have 4 of them. Each of them has a volume of 4/3 pi r cubed, which is 16 over 3 pi r cubed. And so when we define the packing efficiency, remember we take the volume of the atoms themselves, 16/3 pi r cubed. We divide it by the volume of the cube, which is, remember, the length of the side taken to the 3rd power for the volume of a cube. So it's going to be 2 radical 2 times r, the whole thing cubed. We multiply that by 100 to convert it to a percent, and we get 74%. Okay? Now we did packing efficiencies for the other 2 last time. We'll summarize this in a little bit, but the simple cubic was 52%, the body-centered cubic was 68%, and this is 74%. So this is the most efficient packing of atoms that we can have in a cubic structure. All right, can't get any higher than that. Now the last one we'll talk about, but not in as much detail because it's a little harder to visualize, and it's it's not as geometrically friendly, is the hexagonal close-packed cell. So what we're doing here is sort of similar to what we did before. We're starting with the same close-packed layer of atoms, but this time we're doing what's called AB stacking. So we stack 2 layers offset from each other, but this time we're going to put the 3rd layer directly on top of the 1st layer as opposed to doing another offset layer. So it's a little bit different. So it's generated by AB close packing, or ABA sometimes. Some people call it that. But the point is we only stagger 2 layers before putting the 3rd layer directly on top of the 1st. Now the number of atoms in a unit cell so if we look at this view here, is probably the easiest. This is also not easy to visualize, so we're not going to really go into details with this either, but just to give you the number, so there's 6 on the top and 6 on the bottom. So these 12 are then shared by a total of 6 unit cells. When you put hexagons together, you can put 3 of them together in one plane, and then there's the cell on top of that and the cell below that. So each of those atoms is shared by 6 different unit cells. So there's 12 atoms that are shared by 6. And then we have, it's a little bit hard to see in this viewpoint, but there are 3 of these blue atoms that are completely enclosed in the cell. So there's another 3 atoms at the center of our cell that all count individually. And then we have the atoms in the middle of each hexagonal face. So like this one here, for example, is shared by 2 cells, the one below it and the one above it. So there's then 2 atoms that are shared by 2 cells, so they count as a half. And so we get a total of, if I do my math right, 6 atoms per unit cell. So hexagonal close packed has 6 atoms per unit cell. We're not going to worry about this one as much in terms of all these details. I'm just showing you how you get that number. And then also the packing efficiency for this is complicated to calculate because it's a hexagonal structure, so how do you calculate the volume of that? I don't even know, so I'm not going to even try. But people that are better at math than I am can calculate the packing efficiency, and it's exactly the same as the cubic close packed structure, 74%. All right, which kind of makes sense because we're taking close packed layers and we're stacking them on top of each other as closely as possible. So the packing efficiency comes out the same, even if the geometry is more complicated to get to that point. But the point is the cubic close packed and the hexagonal close packed structure, they have the same packing efficiency. The only difference is how they're formed. This is an AB packing where you alternate the layers where you eclipse the layers every 3rd layer. The other one is ABC packing where you do 3 staggered layers before the 4th one. Now, since the packing efficiency is the same, why do some metals occupy a hexagonal structure and others occupy the cubic structure that's equally efficient at packing? That's something that people don't really understand that well. So both of them are available, and different metals are going to have different structures, and there's really no easy way to predict it. Now, the last thing that we want to define about all of these structures is coordination number. Okay, so we have a lot of parameters for these different structures, and then this one is defined as the number of nearest neighbors. Or maybe an easier way to say it is it's the number of atoms that each atom is touching. Let's see the best way to say that. The number of other atoms an atom is touching. Okay, so if we look at, for some of these it's pretty easy to visualize, others not as easy. But if we look at the simple cubic structure, so let's see how many nearest neighbor atoms this one has here, which I've marked with an X. Okay, so in the same layer as it, there's 4 atoms that are touching it. 1, 2, 3, 4. Then we also have plus 1 above and below. So there's a layer right above it that's going to be touching it, and a layer right below it that's going to have an atom touching it. So in total, the coordination number is 6 for simple cubic. That means there's 6 atoms touching each other atom in the structure. For body-centered cubic, it's actually pretty straightforward to visualize because here, if we just look at the atom in the center here, it's bounded by all of the atoms on the corners of the cube, and there's 8 corners. So 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 total atoms touching that atom, so the coordination number is 8. And if you extend this out in all directions, remember that when we build a lattice, we take these simple units here, the unit cells, and we move them around all in 3 dimensions. Every single atom is equivalent in all of these structures, so every atom would have a coordination number of 8 in the body-centered cubic, although looking at the unit cell, it's very obvious to define that for the center one. All right, and then finally for face-centered cubic and hexagonal, they have the same packing efficiency, and they also have the same coordination numbers. It's a little bit harder to visualize for the ABCA packing. So this is going to be the cubic one up here on top. So if we take this atom here, which is shown as a hollow blue, okay, so that atom here, we're going to define all of the nearest neighbors. It has 6 that surround it in the same layer. Now, in the layer below it, if we look at the yellow spheres, which are the ones below this one, okay, we have, so see how this atom here that I marked with an X is sitting sort of in a dimple created by 3 spheres below it. So that would be 7, 8, and 9 in the layer below. Then we have another layer on top, which is going to be 10, 11, and 12. So in total, there's 12 atoms touching each other one. So the coordination number is 12 for the cubic close-packed structure. And then the same thing is true for hexagonal, which in the ABA packing is even easier to visualize because here we have this red one here, which is already marked for us. We have the 6 that surround it in the same plane. We have 3 above it that touch it, 3 below that touch it, again, a total of 12. So both of these have coordination numbers of 12. All right, so I gave you, a lot of details in hopes of helping you understand these structures a little bit better and how they're formed. But the main thing you need to know is going to be on this, on this chart here, which is sort of the differences between them and some of the key parameters. So this is just a summary of all the information we've gathered so far. I tried to sort of walk you through how we get this information, but if whether you really understand this deeply or not, as long as you know the information on this table, you should be okay. All right, so we have simple cubic, body-centered cubic, face-centered cubic, and hexagonal. These 4 basic structures that we're going to talk about. And they all have abbreviations or synonyms we should be aware of. So simple cubic is also called primitive cubic. All right, so that's another synonym for that you might see, so don't be thrown by that. It's the same structure. Body-centered cubic has a common abbreviation, which is pretty obvious, BCC, body-centered cubic. Face-centered cubic is abbreviated as FCC, or sometimes, as we talked about, this is also called the cubic close-packed structure because it's the cubic structure where the atoms are packed as close together as possible. So you also see this called CCP, cubic close-packed. And then hexagonal is often called the hexagonal close-packed or HCP structure. So just be aware of those abbreviations. Some of the problems on the homework or the exams might utilize those abbreviations, so definitely be familiar with them. The other thing that we derived was just by counting atoms and noting their locations in the cell and whether they count as an eighth of an atom, a quarter of an atom, a full atom, whatever. We noted how many there were per unit cell. So they increase as we go across here. So 1 in simple cubic, 2 for body-centered cubic, 4 for face-centered cubic, 6 for hexagonal. Okay, so those are the number of atoms per unit cell. The coordination number we just got done talking about, so just to reproduce it here, they increase again as we go across. 6 for simple cubic, 8 for body-centered cubic, and then 12 each for hexagonal and face-centered cubic. And then finally, the last thing to be aware of, which is one of the key differences between these, is the packing efficiency. That's the percentage of the total volume that's occupied by the atoms, the rest being empty space. So the worst is simple cubic that has a packing efficiency of 52.4%, which we derived using fairly simple geometry in that case. Body-centered cubic was geometrically more complicated, but we got a number of 68%, so it's significantly more efficient. By putting that one atom in the center, you're now occupying most of that available space, or a lot of that available space anyway. And then face-centered cubic and hexagonal, the most efficient ones, are 74% each. All right, so these are the key parameters of the structures that we want to be aware of. And then also we'll want to keep this in mind because when we come back, we'll start at the end of today and talk about ionic compounds, which have 2 different ions per unit cell. These are just the metallic, the atomic structures here. A lot of this stuff will come back to us later on. Okay, but for now we're going to sort of divert a little bit and talk about a couple other types of solids. So we just talked about metallic solids, which they're held together by metallic bonding. They have these very regular structures that we can define for most metals. And now we're going to talk about another related type, which is a network solid. So this, in some ways, is similar, and they can sometimes have similar structures to metals, but the big difference here is that these are covalent bonds. So whether it's a single atom being held together in this arrangement, or it's a compound that can be classified as a network solid, the point is that it's an extended solid, but it's made up entirely of covalent bonds. So one way to think about these in some regards is as just gigantic molecules. Okay, so we talked last time about how molecular, or not last time, but a while ago, how molecular compounds are made up of covalent bonds between all the atoms. And in a lot of covalent compounds that we talked about, especially at the beginning, you have a central atom, you have some outer atoms, and you have this nice well-defined piece. Here for network solids, they're just molecules that just keep going on forever and ever and ever. They almost never end. Although of course they end at some point, but they can be thought of as infinite, or just huge molecules where the bonds just keep going out in all directions forever. Okay, so the bonding here is no different than what we saw in simpler covalent compounds, but it just doesn't stop. So there are some that we'll talk about that are atomic solids. So any non-metal that exists as a solid, a lot of times it can be thought of as a network solid. So the two main types that we want to be aware of are carbon and silicon. And then carbon forms two different types of structures. Okay, so these are called allotropes. I'll define that down here. I don't think we're going to use this word on the test or even in the book, but it's two forms of the same element. And again, in the case of carbon, there's two forms that exist. You're probably familiar with both of them. There's diamond and graphite for carbon. And they have very different bonding, and they have very different properties as a result of that. So what we're sort of going to do in this section, as we give you some examples and some principles about network solids, is talk about how the bonding arrangement has a very large impact on the properties. Okay, so if we have diamond, this is the structure of diamond. It's just tetrahedra of carbon atoms that just go on forever and ever. So if you look at this carbon here in the middle, you have four that surround it in a tetrahedral arrangement. But then it doesn't just stop there. This carbon that I've numbered number 1, has 3 more bonded to it, and this one has 2 more bonded to it, and so on. So it just keeps going on in all directions. But every single carbon atom has a tetrahedral arrangement. Now, as we talked about for molecular compounds, if the geometry is tetrahedral, the hybridization is sp3. And all the bonds are sigma. Okay, so that's just a quick description of the bonding for diamond. And then the other form of carbon that's very well known is graphite. They don't use this in pencils anymore, I don't think, or maybe they do. I don't know. I'm not up to date on the latest pencil technology, but they used to use it in pencils anyway. It's also commonly used as a solid lubricant. It's very slippery. And the bonding here is a little bit different. So here we have hexagons of carbon atoms. That are so they're in flat sheets of hexagons that are all extended, and then we have layers that are stacked together. Now in this case, the hybridization is sp2, so each carbon is bonded to only 2 other carbon atoms in the same layer as it, if it has 3 other carbon atoms, not 2, 3. Okay, so you have sort of this trigonal planar geometry for each carbon, and so it's going to be sp2 hybridized. And because it's sp2 hybridized, you have an unhybridized p orbital, so it's going to be able to form pi bonds. So this has sigma and pi bonds. Now, one point about graphite is that the pi bonds are delocalized. So every single carbon has a p orbital sticking up above and below the plane that can pi bond with the one next to it. So there's not just directional or localized pi bonds, they're sort of delocalized amongst all the atoms. So all of these orbitals sort of overlap with each other above and below the plane, and they make these sort of extended pi conjugations, we call it. So all these pi bonds that just extend out in all directions within the plane. Now that changes the properties as we'll get into, but that is a key difference between diamond and graphite. Diamond is only sigma bonds, graphite is sigma and pi bonds, and then that defines some differences in the properties. Another big difference here is that in graphite we have these two-dimensional sheets of carbon atoms. The sheets are stacked together, but those individual layers are just held together by London dispersion forces, which is a very weak intermolecular force, as we talked about. And that's why graphite is slippery. The two layers are not held together very tightly, so they can slide over each other pretty easily, as opposed to diamond, where everything is bonded to itself very strongly, very rigid and in place, so you don't have that slipperiness or that flexibility. Now, another interesting fact about carbon, which is not important, but I just want to share it with you. Some ingenious jeweler came up with the slogan "Diamond is forever." That's not actually true. So carbon is a little bit more stable than diamond. Graphite is a little bit more stable than diamond. So if you leave a diamond forever, it will convert to graphite eventually. Now, luckily, it's on a much longer time scale than any of us are going to be alive. So for all intents and purposes, it is forever, but it's not rigorously true. All right, so that's a little fact, but not too important. But what is important is talking about the different properties of them, which I've sort of hinted at already as I described the structure. So we want to sort of understand how the bonding relates to the properties. All right, so diamond, as we know, is very hard. It's one of the hardest materials known in the world. It's colorless, and it's an electrical insulator, so it doesn't conduct electricity at all. Okay, so those are properties of diamond. And then graphite, as we already talked about a little bit, is soft and slippery. If you've seen it before, it's black in color. And it's a conductor of electricity. Okay, so those are the properties. Now the hardness we talked about sort of in regards to how the bonds are held together. So diamond is all sp3 sigma bonds, so they're very rigid, very held in place. And we talked about the reason that graphite is slippery is because the individual layers are held together by intermolecular forces that are pretty weak. So that property comes pretty easily. But to understand sort of the color and the electrical conductivity differences, we have to talk about what's called the band structure. Okay, so band structure is, remember one of our favorite topics from Chapter 4 was molecular orbital theory, where when you form bonds between atoms, you have molecular orbitals that are bonding and anti-bonding. Well, in network solids, which are formed by covalent bonds, you have the same story. You're forming molecular orbitals. They extend, in all directions and infinitely because it's an infinite structure. But we can draw very simple diagrams to describe this. So let's start with insulators, which most nonmetal network solids are insulators, although graphite is an exception. So most nonmetals are insulators. Okay, so if we draw an energy level diagram, so just like we did for molecular orbital theory, we're going to draw orbitals from lowest to highest energy. We can draw a very simple picture, which is that down here at low energy, we have the bonding molecular orbitals which are filled. Okay, so these are completely occupied with electrons, and we call this the valence band. And then higher in energy, we have the empty molecular orbitals, and these will be anti-bonding orbitals, although the bonding character doesn't really matter too much. But these are empty in the ground state. And this is called the conduction band. Okay, and then what we should think about then is, okay, in order for electrons to move through the structures, that's what conducting is. We're taking electrons and they're transporting through the compound or through the element. If that's going to happen, remember that each orbital can only hold 2 electrons. So if these orbitals are completely filled with electrons, you can't have electrons moving between the filled orbitals. They can't take more than 2 electrons. So in order for electrons to move in these structures, they have to then jump into an empty molecular orbital. And in the case of insulators, there's a very large energy gap between the filled and the empty orbitals, so it's very difficult for those electrons to move between them and to transport through the structure. Now, if we look at the case with conductors, right, so conductors over here on this side. Okay, same energy level diagram. So in this case, we have our filled orbitals at some energy. So conductors would be things like metals, as we talked about, or graphite. But then the empty molecular orbitals are pretty much right on top of there. There's no gap between them. Okay, so that's what we call, again, the same terminology, conduction band, valence band. But in a conductor, the valence band and the conduction bands are really close to each other, or right on top of each other. So it's very easy for electrons to move between the filled molecular orbitals and the empty molecular orbitals, and then to transport through the network. Okay, so this is the big difference between insulators and conductors, is the band structure and how the filled molecular orbitals have different gaps between them that allow the electrons to move freely or to have a very high energy barrier to moving. Okay, so that's how the bonding of these defines some of their properties. Now the last one we'll talk about, I don't think this is going to be emphasized a lot on the exam, or probably not at all, but it is interesting and it is covered in your books. I want to just spend a little bit of time on it. And these are semiconductors. So the band diagram for a semiconductor is, we have still our valence band, and in this case, there's a small gap between the valence and the conduction bands. So they're not right on top of each other like they are for a conductor, but the gap is also not huge. All right, so we have sort of an intermediate gap here. Which means some of the electrons are mobile. There's the ability for, so when we say a semiconductor, that means they conduct a little bit of electricity, but they're not very good conductors. But there are ways to change the conducting properties of semiconductors and make them better conductors. And there's 2 ways to do that. It's called either N-type or P-type. So for an N-type semiconductor, we're going to dope it with extra electrons. So the most common, well-known semiconductor is silicon. This is what's used in most solar cells that are commercially available today. And if we take silicon and we dope it with arsenic, so that means we're going to substitute some of the silicon atoms with arsenic. So arsenic is to the right of silicon on the periodic table. It has 1 more electron than silicon, 1 more valence electron. So when we replace some of the silicon with arsenic, we're going to have some extra electrons in the structure. So if we draw the band diagram now, we have our valence band. We have our conduction band, which has some sort of a gap involved. Actually, I'm going to draw this. I'm going to exaggerate the gap here just so I can draw this more clearly at the end. We have a gap between our valence and conduction band. The conduction band again is the empty one. No electrons in here. But when we introduce these dopant atoms, in this case arsenic, which has extra electrons, we have to fill additional orbitals now because our valence band can't accommodate all the electrons anymore. We have extra electrons added in, and so we have sort of these extra charges here close to the conduction band, which I'll represent with little dots here. And these extra electrons are very close to the conduction band, so they are mobile. So remember that the mobility of electrons is their ability to move into the conduction band to transport through the structure. We add some extra electrons in. Those extra electrons are now close to the conduction band, and we now have a pool of mobile electrons. Now the other type is p-type. So here we're going to remove electrons or dope with fewer electrons. An example of this is boron-doped silicon. So boron is group 3. It has one less valence electron than silicon. So if we replace some of the silicon atoms with boron, now our compound is going to be, our silicon is going to be a little bit electron deficient. So what we have here then is we have our valence band and our conduction band, just like we did before. But because our boron has less electrons, we're not going to be able to completely fill the valence band anymore. So the valence band is completely filled in silicon, but now we have electron deficiencies, so there's going to be what are called holes in the valence band. So there's going to be some partially filled orbitals. Each orbital can hold 2 electrons, and now we're going to have some that only have 1 electron. And that creates then spaces for electrons to move into, because each electron can then hop into that empty space and transport through the structure. So these are called holes. And basically these are just extra positive charges in the structure. And so when we think about electron transport in these materials, you have these empty spaces here in the valence band. Electrons from lower in the valence band hop into one of those empty spaces, and that's sort of the mechanism by which the charge transports. You're sort of all of the conduction happens within the valence band, and it's just hopping into those empty spaces and transporting. So this is, again, something we're not going to emphasize. It's pretty advanced materials chemistry that's not really going to be a huge part of this course, but it is an interesting topic, and it does relate to the bonding of extended solids, which is something we should have at least a base level understanding of. Okay? Now the last class of compounds or solids we're going to talk about are ionic solids. So we already have a pretty good idea in our head of what ionic compounds are, but we want to sort of understand some more about their structure here. So we want to understand first how the structures are formed. So we've dealt with a lot the forces of attraction between oppositely charged ions, and this is the case here with ionic compounds. So the ions are held in place in the solid phase by forces of attraction between oppositely charged ions. When we first introduced this in chapter 3, I think it was, we sort of thought of it in the context of 2 ions, the force of attraction between them depends on the charge and the radius. But what we want to now start thinking about is that these attractions exist in all directions. So it's a 3-dimensional arrangement of all these ions. They're attracted to each other in all directions. And the structures that these compounds adopt, they're going to maximize those attractions and minimize repulsions. So we're going to try to arrange the ions in the positions that allows the attractions to be maximized, and then minimize repulsions between the like charges. Okay? So in our compound, we're going to have 2 ions. We're going to only really talk about the structures of binary ionic compounds, which is 1 cation, 1 anion, all monoatomic cations and anions. And for these compounds, we're going to have 2 ions. One of them is going to be larger than the other. They have different sizes. So the larger ion is usually the negatively charged one. Remember we talked about when you add electrons to an atom, its radius increases. When you take electrons away, the radius decreases. So typically in our structures, the larger ions are the negatively charged ones, although it doesn't have to be the case. And our larger ions are going to occupy one of the common packing arrangements that we talked about for metals. All right, so it's going to be either primitive cubic, face-centered cubic, or hexagonal close-packed. We don't really see body-centered cubic structures because that would put the negative ion at the center of all the other negative ions, which is a bad place for it to be. But we can have the negative or the larger ions are going to be either in a primitive cubic, face-centered cubic, or hexagonal structure. We're going to talk about the first two only in detail. We're not going to talk about hexagonal in any detail. But that's what we do with one of the ions. And then the smaller ion, which is usually the positively charged ion, that's going to occupy holes in the structure. Okay, so none of these structures are 100% efficient at packing the sphere, so there's some gaps in there. And we're going to fill those gaps with the other ion, which is usually, in this case, the positive ion for the smaller of the two. Now, the structure that we observed and the holes that are filled depends on some factors that we'll get into. So the observed structure and which holes are occupied depends on the relative sizes of the ions. Okay? So depending on how much bigger the larger one is, or the relative ratios of the two ionic radii, that's going to determine which structure forms and which holes in the structure are filled. All right, so let's start getting into the types of holes. We probably won't finish all of these today, so we'll continue on it next time, but let's use a little bit of our remaining time. So the first type we'll talk about are the tetrahedral holes. So if we think about two close-packed layers of atoms, you have three atoms touching each other in one layer, and then you have one that sits above there. And so you have sort of this dimple here in the center that's going to be a gap in the structure. So they're located in a dimple of a cubic close-packed layer. And if we think about then the unit cell, the cubic unit cell, where are they in that picture? There's one of these in each corner of the cubic cell. Okay, and if we look at then this structure here, we have a face-centered cubic arrangement of all the atoms, and then four of them are shown in purple. And then in the center of these four, there's this X here. That's what's called the tetrahedral hole. So it's near the corner, and it's surrounded by four atoms in a tetrahedral fashion, which is why we call it tetrahedral. Okay, so 1, 2, 3, 4. And there's going to be then a total of 8 of those in the structure because there's one in each octet, or each quadrant of the. Can't see today. There's one in each corner of the cube, and there's a total of 8 of those then around the structure. Now, if we want to define the relative size of the tetrahedral hole, we saw earlier that the side length for a cubic cell for a face-centered cubic cell in terms of radius is 2 radical 2 times r, where r is the radius of the larger ion in this case. Okay, Okay, so big R is the radius of the larger ion, and the side length here is 2 radical 2r as we derived earlier. The diagonal of our cube is equal to a times the square root of 3, another geometric argument, which is then equal to 2 radical 2 times radical 3 times big R. So we're going to replace a with 2 radical 2r. And then as we transport through our structure from one corner to the opposite corner, this is a little bit hard to visualize, so don't worry if you don't catch this exactly. But as we go from corner to corner, we go through one radius of the larger sphere, one radius of the smaller sphere. That takes us a quarter of the way across. So as we go through the whole diagonal, we go through 4 of the larger radii and 4 of the smaller one. 1 of the larger, 2 of the smaller, 1 more of the larger, 2 more of the smaller. So it's hard to picture, and this isn't the best picture for doing it. But anyway, the point is that it's 4 times the sum of the 2 radii. Okay, because the sum of the 2 radii takes you to here, to the center of the tetrahedral hole, and you have to do that 3 more times to get to the opposite corner. So a total of 4 times the sum of r plus r. Again, these derivations are not something you're going to have to do yourself, but I'm just trying to help you understand where these numbers come from instead of just throwing them to you on a piece of paper. So what that means then is if we rearrange the structure, we have this now a relationship here between big R and little r. And we're going to solve for little r in terms of big R. So radical 2 times radical 3 over 2 times big R is equal to r plus r. So we divide both sides by 4. And that means our little r is radical 2 radical 3 over 2 minus 1 times big R, which is equal to 0.225 r. Okay, so that's the size of a tetrahedral hole. Now what it means for us is that this is the smallest ion that we can put into a tetrahedral hole. And this is the smallest hole, as we'll see. So this is really as small as we can get. So if our smaller ion, the cation, has a radius that's 0.225 times the larger, it'll go in here. And then we can even expand this a little bit, as we'll see. So if the ion is a little bit bigger than that, it can force the negative ions apart. Because remember, in the cubic close-packed structure, all of our negative ions are touching, which is a bad situation because they're the same charge. So if we put a larger cation in here, we can force them apart a little bit and spread them out and still maintain the attractions between the opposite ions. But this is the smallest radius that can be defined. We'll stop there. We'll talk about octahedral holes next time. And again, we'll summarize all these different holes eventually once we get to the end.
Does the final replace the lowest temperature? Yeah. Oh, no.
Okay, so for the homework that was last Sunday, were there questions from this week?
Unfortunately, yes.
Okay, because I had this smell of oh my gosh, wait, I remember this.
They get messed up sometimes. I don't usually have time to check them over in detail.
It wasn't that many. It was 2 or 3 questions, but.